In this last unit for this course, we will now look at Gaussian channels. And the reason we look at Gaussian channels is because these channels are the closest to communication systems used in practice. And in fact, analyzing Gaussian channels has led to discovery of error correcting codes for the communication channels, and many of these codes are currently in use. The only technical difficulty is that unlike rest of this course, unlike the channels that we have seen in rest of this course, these channels are not of discrete. They do not have discrete input and output alphabet. These are channels with continuous input and output alphabet, and that results in some technical difficulties in the mathematics used to handle these channels. However, we can present a brief treatment of these channels, which is more or less rigorous, but perhaps not completely rigorous. And that's what we'll do in this part. So we will start with what is called the discrete time Gaussian channel. In this channel, the input alphabet X is the real line, and the output alphabet Y is also the real line. And when you send X, you receive X plus some noise. So you receive X plus some noise Z, which is zero mean and has variance sigma square. Okay. And just as we have been doing earlier, we consider memoryless channel. So memoryless channel. Noise, which means, what is the memoryless property here? It just means that the noise added in each use of the channel is independent. Okay. Okay. And therefore, if you use the channel n times, so suppose you send x1 to xn, sent over n channel uses, yield y1 to yn, okay, such that the distribution of this vector y given this distribution of this x, or maybe this way, such that each yi is xi plus zi, where z1 to zn are independent and identically distributed with independent and identically distributed Gaussians with mean 0 and variance sigma square. Okay, that's what this channel is. Now, as before, we would like to understand how many messages can you send over this channel, how many bits of messages can be sent over this channel per channel use. Okay, so if you, as before, we seek to design codes of size m and length n with average probability of error less than equal to epsilon. So given, say, n and epsilon, what is the largest m such that you can find a code of size m, okay, with of length n and average probability of error less than epsilon. So this is the same. This is similar to the capacity question that we had raised earlier. So we want to again characterize the capacity of this channel, which is roughly this question: what is the maximum number of bits of messages that you can send per channel use? Now it turns out that the answer to this question is trivial. Okay, I'll show you how. So suppose Suppose for a message m in say minus m to m. So these are 2m messages, minus m plus 1, 0, m. We transmit the code word x equals to m delta of length 1. Okay, so you just send a single number. Okay, then what's the probability of error? What is the average probability of error? So then maybe I should also, just for completeness, also define the decoder. Add the decoder at the decoder you observe this symbol y, the real number y. You declare the message m such that y minus m delta is the smallest. So you declare the message m hat equals to arg min, the one which minimizes this distance, of m in minus m to m. Okay, that's what you do. So if you look at this scheme, what is the probability of error? The average probability of error for this scheme can be bounded as, so what's the average probability of error? 1 by, how many messages are there? 2m plus 1, say. Summation m equal to 1 to m equal to minus m to m. Probability that m hat is not equal to m, given that m is sent. So what is this probability? Probability that the decoded message is not equal to m and m was sent. Well, this can only happen if the received y, this guy here, is less than equal to, this implies that the received y minus m delta is greater than delta by 2, only when it exceeds delta by 2. So you should see it this way. These are your code words. So you take minus m to m. In fact, you take minus m delta to m delta, and you make this grid. And any 2 points in this grid are a distance delta apart. So if the actual send message is here, this is your m, the only way error can occur is if the received y is outside this interval of length delta around m delta. So this guy is greater than this guy here, delta by 2, at least greater than delta 2. Because if it's less than equal to delta by 2, then error cannot occur. So this implies that this must hold, and therefore this is an upper bound. Okay, given m is sent. So this given m is sent is basically saying that given x equals to m delta. So what is this probability? Now this probability doesn't really depend on m delta or x, because this probability is just that you send some x and a Gaussian noise gets added to it, and the Gaussian noise moves by more than delta by 2. So this is exactly equal to, this guy here is less than equal to, each term is equal, so we don't have to worry about it. Probability that a Gaussian, which is 0 mean, exceeds delta by 2. So what is that probability? That a Gaussian exceeds delta by 2. Okay, that probability is less than, well, there are various bounds known for this, but this one is true. minus sigma square by 4 um, 8 sigma square. Yeah, this is just probability that a Gaussian exceeds t is e to the power minus t square by 2 sigma square. It's less than equal to that. You can this is basically called the Q function, and this is a well-known bound for Q function. Okay, so this is the probability of error that you get, the average probability of error. Therefore, you can send as many code words as you want. Suppose you want to make this less than equal to epsilon. Okay, so this implies that delta must exceed something 8 maybe root 8 sigma log 1 by epsilon. So as long as you keep this delta to be greater than this, you can send 2m plus 1 code words with probability of error less than epsilon. And you are using channel just the once, and you can take this m to be as large as you want. So this implies that you can send as many code words as you want with vanishing error. So this implies that the capacity of this channel is infinity. Okay, so you can send as many code words as you want. So in that sense, this is a trivial problem. So why are we not all using this Gaussian channel to transmit as many messages as we want? Why do we have inherent bottleneck in wireless medium, say? And the answer to that problem is because we were not worried about how much power it will take to send these code words. In fact, the single length code word, length n equal to 1 code word that you form here, all these code words here, they can be of unbounded magnitude, and therefore to transmit them it will take unbounded energy. So a question that is perhaps more interesting, and indeed it has received a lot of attention, is how many bits of messages can be sent per channel use using code words x with average power So these are real vectors. We define their average power as this guy, average power less than equal to p. Okay. So we denote the maximum rate of such code words with vanishing error by CPW. Okay, so we basically are defining maybe CPW. Yeah. So instead of W, I can just put sigma square here because that's the variance of noise here. So the capacity of the Gaussian channel. Okay. So yeah, this is just one line statement. Of course, you have to carefully define this quantity CPW, CP sigma square. First, you will define an epsilon achievable rate, then you will say sup over all epsilon achievable rate. It's exactly the same definition as what we had before, except that we will now we will require that all the code words that you use in your code must satisfy this power constraint here. Okay, this one here. So you define the maximum rate of a code such that all code words satisfy this power constraint as the capacity CP sigma squared. Okay, so perhaps the most famous result from information theory is the characterization of this capacity, and I'll state that result theorem, and this is the capacity of the additive Gaussian noise channel. It says that this Cp sigma square is equal to half log 1 plus signal to noise ratio. So what is the signal power? Signal to noise ratio is the ratio of signal power by noise power. Signal power, average signal power is P, and noise power is sigma square. So that's the formula. Okay, half log 1 plus SNR. All right. So what we will do in the remaining part of this unit is we will prove this formula. But proving this formula requires extending some of the notions that we saw earlier in the course to the continuous alphabet. So we want to, in particular, we would like to extend the notion of mutual information and divergence to continuous alphabet. And we will need also a cousin of entropy, but a rather different quantity called differential entropy. This differential entropy, we will introduce the formula. And unlike how we discovered entropy, discovering the operational significance of differential entropy is a more complicated task, which is slightly beyond the scope of this course. So I will not do that, but I'll give you some idea of what it is about. So that's what we will do in the remaining unit. We will prove this formula by first defining the mathematical quantities that are required to prove this formula. See you in the next lecture.